It's an honor, a true honor, to have Mike Jordan with us today. Mike is professor in the Department of ECS and Statistics at UC Berkeley, and he's been, obviously, as many of you know, an energetic leader, I'd say, at the intersection of statistics and the visions put forth by the founders of the areas of AI and cybernetics in terms of possibilities for computational intelligence. He's worked in both theory and in practical applications. Some of the practical work includes his efforts in genetics and signal processing, information retrieval. We all know about some of the work there, and natural language. On the technical side, he's made contributions, significant contributions in probabilistic graphical models, Bayesian non-parametric analyses, spectral methods, kernel machines, and applications to distributed computing systems, among other areas. Speaking of probabilistic graphical models, I have to say that I first met Mike. I was trying to think about when this was, but a very salient memory.
We both didn't have gray hair at the time. But.
That's for sure. Mine turned gray a couple months ago. I don't know about you. But it was in Corvallis. There was a Bayesian probabilistic graphical model summer school in Corvallis that Bruce Abramson, I think, put together. Right. Well, I think we were all. I taught one course. Teacher, yeah. But Mike was a student. I remember walking out at break, like it was the morning break, and like Michael was the most engaged student in the room. He walked out muttering, "This stuff is incredible. This stuff is incredible." I remember he said that. These probabilistic graphical models are incredible. And I guess it was one of your early exposures, but you were just like ready to, like, we just like were like dry kindling, ready to be lit on fire. Like just at that moment, it was very interesting to see that phase. And another comment you once mentioned to me, maybe you can tell the group this actual story. You said that you were doing X, and I think maybe it was stats somewhere, and you had this chance to go hang out with Don Norman and David Romelhart. And the way the picture you painted, I think it was over dinner one night, is you were like on this out of control kayak going near a waterfall, and you jumped and you grabbed a branch. You said you just grabbed a branch to stop what you were doing and go in a new direction. And that's exactly how you put it. So maybe you can tell us more about my memory there. But anyway, it's really fabulous to have you here. I didn't finish your whole bio here, but let me just say that Michael has received many well-deserved recognitions, and you can read about them in the bio online. And today, Mike's talking about gradient-based optimization, accelerated, non-convex, and stochastic. Take it away. Thanks.
All right. And maybe the most idiosyncratic introduction I've ever had. I wish you could just keep on going. That was very entertaining. Okay, so I'm just going to dive in. I'm a technical researcher, academic, and I just kind of work on the next wave of things. And all of this buzz and hype, I'm a little bit problematic here, is hard to avoid. But I did build a little cottage in my garden, and there's no internet down there, so I mostly can avoid it. But I was recently about a year ago, I was in China, and I'm in the men's room, and the people behind me are talking about deep learning in the men's room, and in a random restaurant in China, and I'm going, oh man. So I finally this week last week I wrote a little blog thing, kind of put a few thoughts out there, just lay them down, and apparently I'm not on social media at all, but apparently it's what you call viral, so it was read a lot. So I will not just jump into my most of my interests. I'm going to say a little bit about this broader picture, and obviously a lot of you know probably even more about AI. I'm not an AI researcher. I'm a statistician. So many of you, with apologies, will know more than me. But I do think that this word is unfortunate. I think it's a great aspiration. I think, at least when I think of Eric and our students, it was the aspiration that we had computers, but can they be made to seem intelligent in some way? And I think it's still an interesting aspiration. Someone turn down the gain a little bit here. I'm getting feedback. Am I only hearing it? It was resonating, high frequencies. Yeah, so we don't have it yet. We don't have it. We don't know what intelligence is, I think. And all these neural nets or things are just taking in data mimicking intelligent. And I don't know if we're going to have it anytime soon. And we don't need it, really, for most things that, there's so many cool things we can do without trying to figure out what it is. And also, a lot of the people who work on, use the AI buzzword these days are interested in autonomous systems, because then it's really, it's really intelligent because no one's telling what to do. And I think that's fine, but it's somewhat misguided too. Really, all of our intelligence should be networked together, and it should be, decisions should be made not independently. They should be made in the context of other decisions and so on. So I think that AI is used too much as just a wild card. You throw it in whenever you need to. And I don't also watch television, but I gather that Mark Zuckerberg went in front of Congress recently. And I gather that whenever he was asked any kind of a challenging question, he'd say, well, AI will handle that. And apparently that happened 16 times in his talk. So there's a little hubris there about computer science saying we can just resolve it, and also let's break things and then later fix them and all that. But when you use AI as an intellectual wild card, that's just not responsible. And I just don't think that we should, in a community, should be supporting that kind of irresponsible dialogue. So I wish we weren't saying AI. That's fine as an aspiration, but already machine learning kind of bothered me because we had this discipline 300 years called statistics, which is the same stuff. But that's well. I lost all those battles. All right, so let me skip over that slide. So in this blog, I said, let's don't use AI for everything. Let's make some distinctions, okay? And there's some historical ones that are still relevant, and then there's ones that have to do with what problems we should be solving, and let's be clear on that. So let's call it human imitative AI. That's kind of where it was back in the origins, and it's like what Turing had in mind. And it's a great aspiration to think about. How do we get this thing that we know is intelligence inside of a computer? Right, but really, then the next few decades came forward, and I don't think very much progress was made on that. We don't really have anything like intelligence yet, but we did have lots of pattern recognition stuff and lots of information retrieval stuff and and algorithms of all kinds. And I think it's mostly IA. It's mostly augment our intelligence. So search engines augment our intelligence, translation systems do, and so on and so forth. And interacting with humans and not replacing human intelligence, but making it somehow more interesting and more deep. That's what's happened. But also, I think what's happened is this thing that's often called Internet of Things by lots of people in computer science. That's just kind of a limited version of it. The real bigger version is the one I think most of us are kind of used to. Is that all around us there's a network of intelligence the system behaves intelligently. It gives us options for transportation. It gives us options for medical care. It gives us options for financial services, commerce, and so on. And we want that overall system to behave intelligently. And to do that, you don't need the individual nodes to be intelligent agents at all. You want the overall system to behave intelligently in the context of human aspirations and goals. Okay, so if we think about that, this focus on vision and speech and NLP and robotics is misplaced because you don't need those for these grander goals. Those are hard problems. They're not solved at all to this day. And focusing only on them makes you not focus on many of the other problems that are really, really important. So I just wrote down some of the ones I've been interested in and working on. I mean, some of them are classical AI aspirations, but many of them are not. So I'm going to talk a little bit about multiple decision making. If you're in the AI world, you think about an agent making a decision. And then maybe you think about a sequence of decisions. That's the reinforcement learning perspective. But the real world problem is you make 100,000 decisions simultaneously for the current medical system all around the world, or for the transportation network or whatever. And how do you control errors across those? You can't treat each decision independently and think about it as a collection of agents. Also, I'm really interested in systems that don't just have data flowing around, but use that data flow to create markets and to create value and make people be able to enter into markets and get things out of it other than just having a platform that they go to. Uncertainty to this day is still not talked about very well about by the machine learning people. They don't seem to care about it because they just think there's enough data that there's no uncertainty, and that's just wrong. Because they've been thinking about domains where like search or commerce, where if you give the wrong answers, no one dies, or no one's hurt, or no one's really inconvenienced. But when we're trying to roll this out in worlds where people do die and get hurt and inconvenienced, then uncertainty matters critically. You tell me some machine learning algorithm analyzed my genome and my current physiological state and says I need to have a heart operation, I'm going to say, how sure are you about that? Should we get some more data? What if this happened? All the other kind of things around these systems. Cloud edge interactions. If you're going to really build something like self-driving car, you need to be able to have local intelligence that's fast, and you need to go up to the cloud for get more computation. You need to communicate. You need to solve all kinds of problems that have nothing to do with human intelligence, but are critical. And moreover, this overall system will have different kinds of knowledge in different cars, and it'll have to get transmitted and made accord. Those are the interesting challenges. Anyway, I could go on. Provenance is one that, the database people talk a lot about, but I think this is really, really critical. You're going to measure data at one place and one time in one situation, and it needs to be used in another place, time, and situation. And you've got to record some information that makes it possible to move it from one place to another and have some reliability about doing that. A lot of my email colleagues just say, well, that's boring. That's not the exciting, Well, no, it's not boring. That's how database people did. They changed the world by building principles that you could build reliable databases, and that allowed the banking system to develop, for example. So I'm still getting a lot of feedback. I don't know if that can be turned down. I don't know if you are hearing it, but I'm hearing all this squeaky stuff. Okay, so let's talk a little bit about multiple decisions. So I'm going to kind of go somewhat quickly through this because the bulk of my talk is some other stuff. But I hope you're all aware that there's this field called statistics, and it studies things like what if I'm going to make errors if I'm making many, many decisions, not just one or a sequence of them. And here's kind of your classical little cartoon. Someone says jelly beans cause acne. Someone says, let's do an A/B test. So I'm going to take 100 people, put 50 in the jelly beans category and 50 in the no jelly beans. 6 weeks later, I look at their skin and see if they developed acne in one condition or the other. And, high probability that didn't happen. And you say, no, jelly beans doesn't cause acne. But then someone comes back and says, well, we got to look deeper. Maybe a certain color causes it. So now they do all the experiments for all the different colors. And what happens is that at some point, by chance alone, the people who already had a bad skin condition get put in the treatment and everybody else in the control. And it looks like, by chance alone, that green jelly beans are linked to acne. And then the scientists get all excited because this is a surprising thing. They publish it. The journals are happy to publish it because it's surprising. The journalists picked up on it. And everybody's all excited about this until it all dies down. All right, and so we're at a wash in this. And again, if it's just journalism and so on, and health, what you diet, who cares? But if it's medicine and finance and commerce and things that really matter, this really matters a whole lot. You hope how many of you all know about false discovery rate? Just to sort of, everybody here, good. This is MSR. That's a good sign. If you take a little 2x2 table of classification table, 0, 1, 0, 1, there's a certain ratio in that's called the precision. Another one is called recall. Another one is accuracy. And there's also another one which is called FDR. It's just in that little table. It's not a brand new thing but it happens to be one that you can aggregate across multiple decisions and get control over the overall fractions of errors in that. So can you control FDR? Well, starting with Benjamin and Hochberg, there was a line of research that's been doing that. And it is real important to know about, but it made strong assumptions. It assumed that you had independence and no logical constraints. And as time has gone on, boy, I'm surprised by. Yeah, let's. I guess that's a video also, though.
The guy is coming. What about the gal? This is the first organization.
All right, if you're using the video, this is not going to help. Okay, I'll just try to not use high frequencies in my voice. No fricatives.
Can I just turn this thing off? Is that okay? Will video still work?
Yeah, that's his video feed. Is there a gain?
I can't touch anything. The AV guys, I hit the button and it's just coming.
People have heard me lately saying that there's a grand AI challenge, which is the killer AV wire I want to create.
All right, I'll just try to, I'll ignore it if you guys will ignore it for a while. Okay.
Stand behind where? I'll stand behind the speaker.
Might help, yeah. That's a good musician's fact. There's been work on removing these assumptions, and I just wanted, this is a piece of publicity. I don't want to this is a separate talk, but we've just written a paper which I think is kind of a very full version of this. You can now have hypotheses that are related by a directed acyclic graph. So if this hypothesis is true, this must be, if there's a logical constraint, and so if you reject this one, you must reject this one. That's being allowed now. Moreover, it can be done in an online matter, that you can start rejecting hypotheses or accepting, and over time, I can stop you at any moment, and your error fraction up to that moment should be under control. And so there's a relatively simple algorithm that does these kind of things. Why am I holding this? All right, but I also want to focus on another side of multiple decisions that's less discussed. And it is about load balancing, and this is where economic ideas, I think, are coming into play. Think about situations where we're making 100,000 decisions, like in a transportation system or a medical system. Now, if there's no scarcity of resources, this is not such a big deal, but in real world, there's almost always scarcity of resources. So think about a recommendation system. Amazon built one, you come in and it recommends maybe a movie to you, and it does that by looking at all the features it knows about you and so on. Now later that day, someone else comes onto the system and a recommendation is made to that person. And those are independently done, right? And suppose it's the case that you recommend the same movie to everybody. 100,000 people came to your site, 99,000 got a certain movie recommendation. That's fine, there's no scarcity. I can stream the same bits to everybody. Right? What if I recommend the same book to everybody? Well, it's a little bit of a more of a problem. If 99,000 people order it, it's going to be a little bit of a problem. Right? Well, we're really not getting to the core of the problem. The core of the problem is something more like this. What if I recommend the same restaurant to everyone? So tonight in Redmond, you all go out and your app says, we recommend this restaurant, based on your profile and all that. By Poisson statistics, there's going to be a good chance that, 400 people get recommended the same restaurant. You all go there and there's a line and no one's happy. No one's getting served. How do you fix that? Well, if you're a computer scientist full of hubris, you say, Zuckerberg type person, you say, well, we just better algorithms, AI, Yeah, well, no, that's not going to really work. We're not going to be able to know how to do that load balancing. There's all kinds of issues that would arise. What if we figure out the best path from here to the airport and we recommend that to you, and to you, right? Well, everybody will go down the same street. All right, and again, you might think no big deal. We can fix that. Those are small problems, right? But they really aren't. And so now think about, I'm building a financial service, and I'm going to roll it out, say, in China to 500 million people, and because people have some money, and I'm going to make recommendations to them. This financial institute, everybody should buy that stock, right? By Poisson statistics, there's a good chance I'm going to recommend 100,000 people to buy a certain stock. I'm going to destabilize the market. And I hope you can. These aren't cartoons. I hope you can see that this is really the core of the problem. Okay, so now how do you fix this? Well, you bring in economics. You don't just treat this as a platform that you build and do machine learning on. All right, you recognize that whenever you've made data flow, you can build on top of that economic ideas. All right, so think about the restaurant situation. What you really need is a two-way market. Okay, so you need that the people in the restaurants have an app, and the people who are the customers have a different app. Right? The people in the restaurant say, tonight I have 50 seats open. There's a wedding in there, but I got 50 seats open, and I prefer people from out of town, and I prefer young people, whatever. I have some policy, right? And so now when I walk out of the movie at 7 p.m., my app says, that restaurant knows about you, and it makes a 10% discount for the next 10 minutes. All right? I look at it and say, oh, great, I accept. And now the other app has filled one of the seats in the restaurant. There's now 49 seats left, and it keeps going until it's full. And then it's an open market. All the other restaurants see that favored restaurant is now full, and it starts making. They start making their own offers. And maybe, oh, big opportunity! I'll make a 30% discount, and I'll fill my restaurant tonight for the first time ever, right? So now data, just by the connection of data, you're able to build a two-way market, all right? And you're able to solve the load balancing problem. It's just gone. Okay. Plus, you'll be able to make connections between business and consumer directly, not between you as a computer science platform and business, or you and computer science platform and the customer, directly between them, and you've created a market. Now, if you want to take your 5% cut, you can make money off of that. That's all good. All right. Now, here's another example. So I'm involved in a company called United Masters. I'm on their scientific advisory board. It's a fantastically interesting company. It's the people really in the music business, but kind of on the musician side. It's easier than ever to make music. People are making really good music on the weekends, not their full-time job, and uploading it to SoundCloud. And then the streaming services are getting that music, and people are listening to it more than ever before, but no money is flowing. No one's making money off of that, and that's a problem because people can't have that as a job. And there's a big loss of opportunity that a market would be able to create. So how do you fix that? Well, you create a market. All right, so this particular company is doing that in the following way. They partner with the people who have the data flow, and for any given budding musician, you're not the top 100 that the record companies have picked up on, but the next 100,000 or 1,000,000, they take each one of them and they collect all the data of all the people who've been listening to them. And then they reveal that to them on a dashboard. So I would see a map of the California, and I would see all the cities this week who's been, how many people have been listening to me, or of the whole U.S. All right, and a lot of these people, they have a big listenership. So if I learn, for example, that for some reason in Orlando, Florida, there's 10,000 people who have been listening to me this past week, somebody liked them and told their friends, then based on the data, I would go give a concert, and I could maybe make $25,000. And if I do that 3 times during the year, I have a salary. And I don't have to drive a taxi during the week and make music on the weekends. I have a salary suddenly. Moreover, there's a connection now, again, between the merchant and the consumer. The musician now knows who listens to him or her, and they can make offers to them. I'll play your daughter's wedding for $10,000, or you can come backstage, and so on. So I now have a market, and I can price things and compete and have points and loyalty programs, and you name it. And now people can have jobs, right? We don't have musicians who have jobs mostly right now. I know a lot of musicians, and none of them have jobs, except the top 100 like Beyonce that are getting promoted to death. So computer science can be done to do that if you partner with economics. And data science, data, is the thing that glues it all together. Okay, I think I'm going to skip this other one. It's another kind of business about economics. Yeah, I think I'll skip this one. Okay, so I had a list of challenges there, and I picked a couple that I just want to talk about that brought up some themes. And these are really things that I'm currently interested in and working on. Okay, and so I don't have results per se to talk about, but I'm quite convinced the results are going to come. Let me talk a little bit about now. Turn to the core of what I promised to talk about, and so we're going to be linking statistics and computer science. So I am really an academic. I don't want to just do this in an ad hoc way and create something that kind of works, but I want to understand the fundamental principles. I'm particularly interested in lower bounds more and more these days, because that strips away all the inessential stuff and lets you focus on the essentials. And I don't think that machine learning has achieved what people think it's achieved, that it blended statistics and computer science in some deep way. I think it borrowed ideas from here or there, kind of put them together willy-nilly. But there's no foundational principles that have emerged by bringing those two together, and we're missing those foundational principles. So in particular, data analysis problems have a time budget. So you need to be able to say something like, well, like in finance, it's microseconds, in search or, internet, it's milliseconds, in medicine, maybe it's hours, but there's always time budget. And the idea that you control risk under a time budget is just not familiar to either statisticians or computer scientists at a theoretical level. Okay, so how do we start to do that? So I think many of us who work in this more theoretical branch of the field think that optimization has provided the best help with this, especially if you're thinking about lower bounds and complexity results. Computer science doesn't have hardly any lower bounds, and most of the ones that you have are kind of meaningless. And it's because the computer science model is too strong. Turing complexity is just too strong. It tries to do everything. We need to do not everything, and we can get more meaningful bounds. So optimization theory does exactly that. So it's provided algorithms and insights. Statistics also has a lot of good lower bounds. I mean, you've heard of Kramer-Rao lower bound, but there's a lot of others. And they have been very important for this older field to progress. And so taking statistics lower bounds and meshing them with optimization lower bounds is turning out to be very productive. Okay, moreover, used to be, I learned optimization in the 80s, and it was taught as a finished field. There was simplex and gradient and conjugate gradient, it was just done. There was software for all of it, and it was just done. All right, and that's turned out to be completely wrong. All the new problems that we were getting, and plus the kind of perspectives that arose out of the Soviet Union with gradient-based methods have really changed everything. All right, so in fact, those of us who work on this focus on really simple algorithms that can work in a computer science scalable sense. So we restrict ourselves to gradients, no Hessians, at least for now. That'll probably change. We do stochastics because it's cheaper and our data is noisy anyway. And then we work on acceleration because the geometry matters, and acceleration allows you to bring in geometry, and it also allows you to achieve some of the lower bounds that I was referring to. And then how these things all interact in a detailed way is what a lot of us are working on. And let me acknowledge a couple of people in the room. Ji-Wan, who I met this morning, has worked a lot on these things, and Shi-Jin, sitting in the front, is a student with me at Berkeley who's an expert, and I'm going to be talking about some of his work. But many others. This has been a topic that I think is our field of machine learning is very, very popular these days. A lot of people think deep learning is everything, and I have nothing against deep learning. It's great. But at the same time, there's just been just as much progress, if not more, on this theoretical wing, and it's less aware, but people here and other places have been doing this. Okay, so I learned from Chi that the bad local minima, which I thought were the core problem when you went to non-convex problems, are not so bad after all, maybe. at least in a wide class of problems. So there's a lot of architectures which in the last few years people have proved have no local minimum at all. They have a single global optimum and then a ring of saddle points around that. And so it's really saddle points that are the problem. And you should think about a saddle point. There's sort of a lot of directions where you're coming down, but then you go back up again. And there's only precious few directions that allow you to get out. All right. Now, why is that a problem? Well, in 2 or 3 dimensions, it wouldn't be a problem, but in 100,000 dimensions, it's very, very hard to find that direction that leads you to get out, and it could take a huge amount of time. And in fact, when you train neural nets, you see the error rate comes down real fast, and then it flattens out, and then you wait for some indeterminate amount of time, and then it comes down again. You're in a saddle point, and you probably hit a couple of saddle points. Right? And so we need, if we're going to really understand anything about how long it's going to take to train these things and how, as things get larger and larger, we need something about the dimension dependence. Okay? So not just rate of convergence, the classical thing, after how many iterations do you need to be within epsilon of the optimum, but as a function of dimension as well. Okay, so there's a saddle point in 2 or 3 dimensions. We're going to be interested in how do you escape it efficiently, meaning efficient in a computer science sense, and specifically getting the dimension dependence. Kind of naively, you might think it'd be exponentially. You kind of have to search all combinations of directions. Right, so this is work with Chi and some others, Orongu, Sham Kakad, who's here in the city, and Pranit Netropali, who's at MSR, is that correct? Yes, in India. Okay, so here's a little bit of background that led to this particular line of work that I want to focus on. In joint work with Jason Lee and others, we were able to show that gradient descent asymptotically will never end up in a saddle point. Fitting one's intuition, but this has been an open problem, actually. For gradient flow, which is the continuous version of gradient descent, it's the differential equation x dot is equal to minus the gradient. That's been known for like 100 years based on Morse theory that it asymptotically avoids it, but that's asymptotics. And it's been open for gradient descent, the discretization of gradient flow. So that sounds good, but then there's a negative result with, again, Chi Jen and Simon Du, that gradient descent can take exponential time to avoid saddle points. Okay, so there's a class of functions which aren't that weird, where it does take exponential time. So it's something of a surprise that Chi and some others proved a theorem in 2015 that showed that if you add stochasticity of a certain kind, you go from exponential down to polynomial. All right. Now that result still left us a little bit short of the explanation of why gradient descent is so effective and stochastic gradient is so effective. It's just polynomial. It could be, high degree polynomial. Okay. So the goal in this line of work was to prove a stronger theorem. Okay, so to get started, let's talk about convex optimization. F is convex. Let's look at gradient descent. There it is. Go downhill in the gradient. And it is a fact that you get convergence to a global minimum under very, very weak conditions. And moreover, more importantly for this talk, the number of iterations to get there is independent of the dimension. That's less well appreciated. And it's kind of an amazing fact. You can be in infinite dimensions, and the number of iterations to get the optimum is the same as if you're in finite dimensions. Okay. So some caveats there, but that's basically true. Now let's go on beyond beyond convex problems. Let's go to the non-convex world that people like Sebastian helped us get into. So here we can have local maxima, we can have saddle points and local minima. So what can we say about that world? Okay, so first of all, just briefly, this is that list, and it's probably gotten longer, of non-convex problems that have only provably have a single global optimum, and they have saddle points is the problem. Okay, so an interesting list. It doesn't include neural nets, but it includes lots of other interesting, important problems. Okay, so let's just set up the basics theory, the classical case for gradient case, and then move on to the non-convex case. So for the classical convex case, one talked about a simple smoothness assumption. The gradient doesn't change much, the kind of the minimal assumption you can make. And then you attempted to prove that an algorithm would converge to a first-order stationary point. So that would be a point where the gradient is equal to 0, classical stationary point from calculus. And then we put a little epsilon ball around that so that we can get a rate. So you can do it for different values of epsilon. You can talk about the rate at which you're approaching the optimum. That's why the epsilon is there. So it's called an epsilon first-order stationary point. And here is an example of a result due to Nesterov, which shows that the convergence rate is 1 over epsilon squared. Which is polynomial rate. It says if you want a really small epsilon, the number of iterations is going to be more. It's going to grow. This is the initial distance to the optimum, and that makes sense. If you're far away, you got to get there. It's going to take that amount of time. And there's your Lipschitz constant. No dimension dependence. That's the amazing thing about this algorithm. No dimension dependence. Okay, what about going beyond that? So let's go now to the non-convex case. So first order stationary is no longer an appropriate criterion because saddle points are first order stationary. And we don't want to hit saddle points. So we need to go beyond that. Let's define a notion of second order stationary, where the gradient is again 0, or you put a ball around that to get a rate, and the minimum eigenvalue is greater than or equal to 0, but again, you let a little slop, you let it go slightly negative so you can get a rate. And this is a particular parameterization of that amount of negativity. That rho is a Lipschitz constant. Now for the Hessian, we need to make a little smooth assumption also on the Hessian, because if the Hessian changes wildly, you're not going to be able to converge out of a saddle point. Okay, so this is the original paper doing this. There's been some work since then, but this is kind of a minimal algorithm, a simple algorithm that can be analyzed theoretically. So it's just gradient descent, but from time to time, sporadically, you add uniform noise from a ball around your current iterate. You do that when the gradient is small, but you don't do it too frequently. There's a parameter t, which says you only do it once every t steps. This can be removed, and the particular choice of uniform ball is not essential, but the basic idea of having to have stochasticity is certainly necessary. We saw the exponential rate before, and this is just an example of an algorithm that can be analyzed relatively simply. Okay, so here is the theorem from this work by Chi-Jen et al. And it's so the number of iterations under all these assumptions to find a second order stationary point now, not first order. It looks exactly the same as the Nesterov result. It's 1 over epsilon squared, distance to the optimum, Lipschitz constant. And the only difference is that little twiddle right there, which is a standard theoretician's trick for hiding the dimension dependence. But we don't want to hide the dimension dependence. The whole point of this talk, so we're being honest about it, and there it is. It's polylogarithmic in dimension. So it's not polynomial, it's way better than that. It's logarithmic, effectively. Okay? That 4 is probably an artifact of a particular proof technique, but it's probably logarithmic is the truth. But it is logarithmic. Okay? So that, I think, is perhaps one of the first convincing reasons why you should think stochastic gradient should work well in high dimensions, because its dimension dependence is so favorable. The proof technique here basically involves, in some sense, some differential geometry. Around a saddle point, there is a region, the Hessian is varying, so there's a region where if you're in that region, it's hard to get out of it. The flow due to the negative eigenvalue doesn't hit you fast enough, and you're sort of stuck for a long time. All right, so you need to measure the width of this region, and this paper used a coupling technique from probability theory. It said, I don't know that width, but I start 2 coupled diffusions that are a width r apart, and then vary r until you get a phase transition, so when they start to fly apart from each other. At that point, you know the width. Okay, so you don't just have to do kind of a replace this with a flat slab, which had been done in the previous work to get the polynomial dependence, and this logarithm comes out of that argument. Okay. All right, so with that as background, there's a few key ideas that emerged in this that are going to be allowing us to look at some other problems. So first of all, I haven't said anything yet about acceleration. Again, there's some real experts in the room. And as they will tell you, acceleration is pretty important if you're going to be a theoretician. It adds momentum to the problem. It allows you to achieve some of these oracle rates. And we want to bring it into contact with these other ideas. So here's been an open problem. If I'm arriving at a saddle point, is it possible to kind of blaze past the saddle point because of the momentum I've built up? Or is momentum not independent? It's sort of not help me with saddle points. Can we use other kinds of stochastic models, not just this one? And if we go to kind of full stochastic models, we start talking about diffusions and how do diffusions interact with the kind of this convex and non-convex geometry. So all kinds of new problems can be start to look at. In my group, we have gotten a lot of help by thinking about these problems not in discrete time, but in continuous time. And so that's probably the big message of my talk is that if you thought you could avoid differential equations and you went into computer science to avoid differential equations, I'm sorry to tell you, you're going to have to learn about differential equations. All right, now why? we're trying to develop fast algorithms and algorithms that we know how fast they can be, and what's like we want to analyze like what's the fastest rate. And so what does it mean to have the speed of an algorithm? If I'm just hopping along some discrete points, what does it mean to hop faster along those discrete points? Well, it means you've embedded the problem in a continuum of time somehow. Okay? All right? And if you're going to embed the problem in a continuum of time, you have to start talking the language of differential equations. Okay? So this line of work has done that, and it's gone pretty far at this point. So I'll tell you a little bit about variational, Hamiltonian, symplectic perspectives. Andrew Ribison is now a postdoc, but he was a student with me, and Aish is still a student with me one more year. And they played a major role in developing this work, in particular the variational and Hamiltonian framework. And then Aish has gone quite a bit further with Lyapunov perspectives on all of this stuff. And then on this symplectic work, Mike Betancourt has joined us from Columbia to help out. Yeah, so this is about embedding optimization problems in continuous time. And once you've done that, you learn about why algorithms behave certain ways in discrete time. Okay? There's going to be phase transitions happening only in continuous time that you would never have seen just in discrete time, or with great labor. Okay? So let me say something a little bit kind of grandiose sounding. But if you look at the fields that are mathematically the most mature, they make serious usage of the fundamental theorem of calculus. There are some differentials, and there's also some integrals. All right? And fields that aren't so mathematically mature, they picked one or the other. All right, so physics is the poster child for this. You know, Newton wrote down F equals ma, which is laws of nature using derivatives. It's a differential equation. And then Lagrange came around about 100 years later and said, I can rewrite all that physics using integrals. I'm going to integrate an energy, and then moreover, he introduced optimization. I'm going to optimize the integral of the energy, and I will get out the same physics. Probability theory is full of this. Talleyrand's, smart paths are this. Feynman diagrams are this. Statistics has, Laplace expansions and saddle point expansions. So anyway, all of this is really just fundamental theorem of calculus used in elaborated ways. The numerical disciplines also. Finite element analysis is you take a PDE and you discrete little patches using integrals and relate those integrals to each other. Monte Carlo is trying to do integration by using derivatives inside of the integral, and so on. So you can now ask about optimization. Is it one of these mature fields? As I alluded to earlier, it was kind of thought of as done, right? So it's not done, and in particular, it's only focused on differentiation. You'll open up paper after paper, and there's all these derivatives, and there's there's inequalities based on the derivatives, but there's almost never an integral sign. It's just some Taylor expansion of something you're ignoring, but otherwise it's not really fundamentally part of the field. So I would argue that the field is not mature yet. Okay, so let's now again fix ideas by looking at a simple situation. Let's talk about convex optimization again, smooth convex optimization. Here's gradient descent again. And now here's a new fact that if you're a theoretician you know, but otherwise you might not, is that not only does this algorithm have a specific convergence rate for a particular function, over the entire class of convex functions it has a convergence rate. And that rate is here, so this is a worst case rate. It says that after k steps have gone by, you are within 1 over k order, 1 over k of the optimum. Okay, so that's a convergence rate for the entire, so it's a complexity result, really. Okay, so once that was known, and it's probably been a few decades now, the Russian school, Arkady Nemirovsky in particular, asked a very interesting question. They said, is there a general complexity result here? Is there a lower bound for this class of algorithms? Now, what does that mean? Well, first of all, he had to think about what kind of computer am I talking about to get a lower bound. So when we look at all possible algorithms, I have to talk about the platform. And if you talked about Turing complexity at this point, that wouldn't be very helpful. The lower bound would be sort of 0. You just look at the description of the function and figure out the answer. All right, so it had to be a more restricted family. And so he said, well, I'm just going to allow you to look at the gradient, and I'm going to allow you to keep all previous gradients, and your updates must be in the span of all the linear span of all previous gradients. So it's a very powerful machine, but it's not Turing complete, but you can make progress with it. All right, and so after doing that, he said, in this family for smooth convex functions, what's the best you can do? And he proved that it was 1 over k squared. It was faster than gradient descent. So there was an open period of time where no one knew whether it was an algorithm that could beat gradient descent and arrive at that lower bound. So it was something of a surprise when Yuri Nesterov in 1983 wrote down this algorithm, which has got 2 pieces instead of just 1, and it achieves the lower bound of 1 over k squared. And so it's kind of some amazing facts about it. Well, first of all, it is kind of a gradient descent thing. The y variable, there's two variables now. Y is using the x gradient. And then the new x is kind of a linear combination of the previous two y's. So it's got this heavy ball or momentum flavor. There's like a little bit of implicit here. But it's a bit of a mystery where this comes from. But it's no mystery that it does achieve this rate. Okay, that's really amazing. Moreover, one of the mysteries is that this thing is not a descent algorithm. It can go down and then go back up and go back down again. That seems strange if you're trying to get down to the bottom as fast as possible. And gradient descent is the steepest descent, so how can you beat it? But you really are beating it. All right, so again, I think you got to go into continuous time to understand this. So let's start with going into continuous time, which is gradient descent. So here's the gradient flow. It's widely studied by the mathematicians still to this day. And you can analyze the rate of convergence of that for convex functions. The rate is 1 over t, okay, corresponding to the 1 over k for gradient descent. All right, so now you can ask, what if I take the Nesterov equation, which has 1 over k squared, and I take the step size to 0 and get out a differential equation. You will get out one. Here's what you get out. This was done by Sue, Boyd, and Candes. And you can analyze the rate of this, and it is 1 over t squared. Okay, it's an interesting equation. It's second order, no surprise because you had two equations. There's a mysterious 3 here, and there's a damping term. And there it is. There's the differential equation for Nesterov. All right, so we looked at this and said, that's an interesting differential equation, but where does that come from? Why is that the best differential equation? In what sense, why is it giving you the optimal result? Okay, so it's a little bit like Lagrange looking at F equals ma and saying, that's a great differential equation, but why that differential equation? Where's it coming from? Is there an energy principle that allows us to derive that differential equation from some principle? Okay, so that's what we worked on, and we have a paper about a year and a half ago in PNAS, and I'm just going to show you the answer, at least our answer. Our answer was to write down the following Lagrangian. So it's in continuous time. The alphas, betas, and gammas are not the important part. They're just degrees of freedom that give you a family of algorithms, not just one algorithm. All right, we'll set them in particular ways. So that's just time scalings. The important part is this thing right here, which is called a Bregman divergence. Hopefully most of you know what that is. Here's the math of a Bregman divergence, and here's the picture. You're trying to measure distance between x and y. You do that by writing out an auxiliary function h, and you take the linear approximation of h at x, and you look at the discrepancy at y. So that red amount there is the Bregman divergence. It measures the distance on the x-axis by using this vertical distance. If h is quadratic, this just becomes Euclidean distance between x and y. This is just a variational way of writing out Euclidean distance. But h could be logarithmic, and all sorts of other things are possible. All right, and so we're going to use the Bregman divergence in a novel way. We're going to measure Bregman divergence between x, where we are now, and x plus a time-scaled x dot. So it's kind of a little bit of like an elasticity, if you will, or an energy along the direction of the flow. So think, in fact, of this as like a kinetic energy, and then we take a time-scaled version of the function we're going downhill on. That's like a potential. We want to go down on that. So this is like a kinetic minus a potential, a Lagrangian. Moreover, if you set h to quadratic, this thing reduces to 1/2 x dot squared. So it literally becomes the classical kinetic energy, and this is literally Lagrangian. It's a time-varying Lagrangian because we want to not just oscillate around. We want to end up at the optimum. Okay, so what do you do with Lagrangians? Well, you put them inside of an integral, and you optimize over paths. All right, and that's what we do here. So we put it inside of an integral, and then we optimize over paths. So we'll now compute some path, and we'll compute a dynamics along that path. All right, and the way you get all that is by a differential equation. And how do you get that differential equation? Well, you set all the partial derivatives equal to 0, essentially, the continuous time version of that. That's called the Euler-Lagrange equation. So I just hit that object with some derivatives, and out will pop a differential equation, and I will do it. This is our master differential equation. Here it is. I claim this describes a vast family of accelerated methods in continuous time. It has an x double dot, it's got a damping term, and it's got a bunch of geometry right here. If you set h to quadratic, and if you set alpha and beta as logarithmic in t, then this whole thing reduces to that Sue, Boyd, and Candes differential equation with the 3 over t and all that. But this also gives you a whole bunch of others, mirror descent acceleration, cubic regularized Newton acceleration, and a whole bunch of others. So in some sense, it is capturing this family in continuous time. Right, next question. Does it give you anything more? All right, does it, for example, give you convergence rate? Okay, because usually convergence rates are case-by-case basis. That's a couple of pages of, Cauchy-Schwarz and Jensen's inequality and so on. And so it's a pleasant surprise, and I think it's helped us feel that we were on the right path with this line of work, that there's a one-line proof of convergence. The convergence rate is big O of e to the minus beta t, where beta t is a degree of freedom you get to set. Okay, I'll talk about that in a minute. And the proof is just you write down a Lyapunov function, again using the Bregman divergence. You take its first time derivative and you ask that that be negative. That happens if and only if this is true. So there's how I get a convergence rate once and for all. Okay, and again, Aisha has worked a lot on Lyapunov functions. She's not only worked with this one, but also done the mapping between discrete and continuous time Lyapunov functions, kind of getting rid of the Nesterov estimating sequence techniques, if you will, or replacing them. Okay, now at this point it starts to become interesting, because this suggests that you can achieve any rate you want to achieve. I said beta of t was a degree of freedom. Okay, so suppose that I know a little bit about convex optimization. I don't expect to get an exponential rate. That seems not plausible. Okay, so I'm going to be not ambitious. I'm going to set beta of t to, say, logarithm of t. And then the logarithm kills the exponential, I get 1 over t. I know that gradient flow achieves that. All right? So let's see if I would recover gradient flow. Well, I just take that definition of beta, I plug it back into the Euler-Lagrange equation, or my master differential equation, and I solve and I get gradient flow. Okay, now Eric comes along and he says, I can go faster. I'm going to set beta of t to 2 log t. So I get 1 over t squared. He puts that in the Euler-Lagrange equation. It delivers that Nesterov accelerated method. Okay, no derivation, just the math does it. All right, she says, no, I want to go faster. I want t cubed. So he puts in 3 log t, and he actually gets out a differential equation that converges the rate 1 over t cubed. Okay, and Jaewon comes along and says, no, I'm going to do it exponentially. Look, the math permits it, so I'm going to do it. So I'm going to set beta of t just equal to t. He will do that. He will get an Euler-Lagrange equation. He will get a differential equation. And in continuous time, he will flow along at that rate. No problem. Okay? Now, here's what's interesting. All 4 of us will go along exactly the same path. Right? It's just that one of us will go slowly along that path, one will go faster, and he will zip right along. All right? So in continuous time, acceleration is it's not the rate that's interesting, it's the path. It's about this particular geometry of this path, the global geometry. Okay? It's the path. And why is that happening? Well, because this Lagrangian is covariant as a differential geometry operator. That's why. Okay, now, so this actual speed we go just means we're using different clocks. Okay, and who cares, right? Just, he uses a slow clock, I use a fast clock, and so on. He uses a super fast clock. So it's like Einstein says, the clock actually doesn't matter. It's not interesting here. Okay, what is interesting is the path. Now, but here's where it finally gets really interesting, which is that Eric and me and Chi are going at these rates. We know that we can achieve ours. Chi-Jen is being a little more ambitious, but he can actually achieve 1 over t cubed. That's a discovery here. And he can't, in the sense of going back to discrete time. He can't put this on a computer. Okay, so what's going to happen is that somehow his differential equation cannot be discretized stably. Okay, so that's now a mystery. At least a year ago it was a mystery. Why can't we discretize the dynamics when we're using these fast clocks or overly fast clocks? We know we can't, because if he could discretize it, he'd beat the oracle rate. Can't do that. Right? What happens when we arrive at a clock speed where we can discretize, and then how do we discretize once it's possible? All right, so I have some theorems on this. They're not completely done in the sense I'd like necessary and sufficient conditions. These are mostly sufficient, right? But they all are coming out of the perspective known as symplectic integration or symplectic geometry. How many of you know about that already? Yeah, 1. I hope you know about it. Yeah. Better. How many of you know what the FFT is? Yeah, so it's amazing. Somebody gives you way more important than the FFT. Yeah, so so I'm going to say a little bit about what it is. I think I have a slide on it. Yes, here it is. So this is a very important area. Mathematics departments have symplectic geometries in them. Every mathematics department has some of them. It came from the late 1800s when people like Hamilton, Jacobi, and Poincaré, some of those luminaries, were asking a very interesting question. They said, we've got a whole bunch of differential equations lying around from physics, like Maxwell's equations, Newton's equations, fluid flow, and so on. We know that they have some, they're not just differential equations, they have some laws that if I flow along the exact flow, I conserve like energy or momentum or volumes in phase space. All right. Now, this is before computers where they were asking the following question. What if we have to discretize this to get an actual algorithm? We're now going to hop along the flow, and not quite along the flow. We'll be a little bit off, right? But is there a way to do that approximately such that you exactly still conserve the laws of physics? You conserve the momentum, the energy, and all as you do this approximate path. All right. It's amazing that they asked this question, and they answered it. And so this area of symplectic integration does this. And so I've spent a year reading on about this. Here's the basic short version of this, that normally you think of a vector field, of differential equations, a vector field. I'm moving along, I'm at a point, a vector is leaving that point, and I follow that vector a little bit. And then I go to the next vector, and I stitch this along. Symplectic integration is a different perspective. It says that at any given point, there's a triple of vectors, and that defines a little volume element. And as I move along the flow, that volume element will shear, but I want the actual volume to stay constant. Can I do that? Well, the volume is a little determinant. It's an alternating form. So I have now alternating forms on a manifold. And Poincaré worked on that, right? And it turns out you can do it. You can exactly conserve these little volume elements. And the integrators that do this are not Runge-Kutta or Euler or whatever. They are a mixture of implicit and explicit. There's implicit Runge-Kutta and explicit. If you do one or the other, you're not symplectic. But if you mix them in a particular way, you're symplectic, right? Meaning that you conserve these quantities. Right now, this seems pretty far away from acceleration and certainly very far away from AI, but it's not. So when you conserve these quantities, an additional benefit is that a bunch of higher order terms vanish because the symmetries are being conserved. That means you can move much faster. You can take much bigger step sizes, and that's the connection to acceleration. Okay? You can take much faster step size, even optimal size steps. All right. So, so long story short, now there's a mathematical recipe that starts from an optimization problem. It writes down the Bregman Lagrangian. Now we're going to go into the Hamiltonian formalism. It's just an easier way to develop symplectic integrators. So there's a standard physics recipe. You take a Lagrangian, you do a Legendre transform. Conjugate duality goes over to a Hamiltonian. This Hamiltonian is time varying. We want to get a time invariant one because that's the easiest way to develop symplectic integrators. So we do a standard procedure called lifting. We introduce a time variable and its conjugate dual, put them in as explicit state variables. Now we're in a space in which the Hamiltonian is time invariant, and you just run a symplectic integrator on that off the shelf. People in real physics that simulate the cosmos or proteins or whatever only use symplectic integrators. They do not use anything else. So there is standard software and standard methodology for doing this. Okay, so let me show you a picture of doing this. This is just a particular high-dimensional optimization problem, particular function. We didn't have to think at all. We simply plugged in the function, Euler-Lagrange equation, Hamiltonian, symplectic integrator, put it on a computer. And you see it converges. It is oscillating. It goes up and down, as predicted. And we are achieving an oracle rate. Okay. If I didn't want to spend much more time on this, but if I put Nesterov next to this, Nesterov roughly is the same. It has a phase near the end which it goes a little faster, which I could talk more about if people are interested. But now if you turn up the step size, Nesterov goes unstable, and this thing stays stable, down to a factor of about 10. We can get a 10 wall clock improvement with this algorithm. Okay, now I'm going to go back to work with Chi again. Now that we have some ingredients, we can put these together. Yeah, please.
You mentioned so implicit and explicit things.
Yeah.
So computationally efficient to compute implicit.
Yeah, so you do what's called splitting. You take this a big old Hamiltonian, you split it into pieces, and you make sure the implicit part is easy to do. And a typical way to do this is what's called a leapfrog integrator, where the implicit part is actually not so complicated. But absolutely, if you split wrong, you can have the implicit part be a load. Okay, but it's part of future research to kind of characterize cases where that's not the problem. Okay, so I'm going to try to finish up here in a couple of minutes. I'm sliding into the optimum here. So an open problem has been, does acceleration help you get past saddle points? I mentioned that before. And taking this continuous time perspective, this Hamiltonian perspective, if you will, helps be able to answer this question. Okay, so let me just kind of skip a little bit. These are some slides I actually borrowed from Chi here. Let me just skip over this. Okay, we're going to be interested in this setting that we've talked about already, smoothness for gradient, smoothness for Hessian. And we want to bring in acceleration now and hit second order stationary points. So setup is the same as before. And here is an algorithm that you can analyze. It basically just, I don't want to get into details, it's gradient descent, it's this perturbation as well, and it also is an accelerated algorithm. Okay, it accelerates and perturbs. And here is a theorem which says that the rate now goes down from epsilon squared to epsilon to the 7/4. So proof that just pure acceleration does help you to get past saddle points. The O tilde, again, is a polylogarithmic term in dimension, so that didn't go away. Here is the Hamiltonian that was used in this particular paper. It's actually a simplified version of Hamiltonian, and I won't get into details, but that was key in getting the theorem here. And then last two slides, now let's start, this is ongoing work, is trying to bring this into the world of Markov chain Monte Carlo and try to contribute there. So to do that, we're going to study, first of all, this is work with Shang Zheng and Peter Bartlett and Niladri Chatterjee at Berkeley. We're going to try to accelerate now not just gradient flow or gradient descent, we're going to try to accelerate diffusion, stochastic processes that sample, like Markov chain Monte Carlo does. There have been negative results on this because diffusion has got a lot of noise, it's Brownian motion. And trying to accelerate Brownian motion is not so easy. But those results have been on what's called overdamped Langevin in the physics literature. Overdamped diffusions. This is just that you take the gradient and you add Brownian motion. It's like gradient descent, but not just pure stochasticity, it adds Brownian motion directly to the gradient. All right, so we've just seen that these momentum kind of methods are able to go faster. All right, so what if we go to a more momentum version of Langevin? All right, so here it is. This is classical Langevin. This is stochastic differential equation notation. It just takes the gradient, goes down and adds Brownian motion. All right, we're going to look at an underdamped Langevin where you add Brownian motion to the velocity and then you integrate the velocity. So the noise, the bad noise that occurred by the Brownian motion is getting filtered. Okay, and here is my last slide. So there has been beautiful work in France on analyzing, finally, kind of finite time convergence results for Langevin. It goes as dimension over epsilon squared, and for underdamped, our paper shows that you go all the way down from epsilon to epsilon squared to epsilon. Okay. And again, in this, the proof here needs this continuous time Hamiltonian perspective to go. Okay, I wanted to skip that. Yeah, so I'm basically done. I did want to give one of my two minor students wanted a bit of publicity for this project called Ray. We have on my list of other topics to work on is a large, long list of things that are kind of engineering or systems, computer system stuff. And so part of my career the last 10 years has been investing in having labs with computer scientists who are systems people, not AI people, including people like Jan Stoika and Dave Patterson and so on. And we've had several labs now, the AMP lab, the RISE lab, the RAD lab, that have been real success stories. And I would give a separate talk on that. Just let me note that Spark came out of this lab, kind of the interaction between machine learning people and systems people. And we have a new project called Ray, which is kind of Spark for reinforcement learning. Spark is a block synchronous paradigm where you parallelize, and each parallel thread or process has got to kind of roughly run the same amount of time. If you do rollouts and reinforcement learning or stochastic search, some rollouts take a long time to decide it was a bad idea, and others take a very short time to decide it was a bad idea. And so you have this heterogeneous workloads, and Ray attempts to, or does, accommodate that. So here's the author list: Philip Moritz and Robert Nishihara, students working with me at Berkeley, and then Jan Stoika. And let me just cut, I want to just say this exists, and I'm not going to show you, that's there what I want to show. It is an open source project, and it has now some contributors throughout the world, and you can now put it on your laptop within 5 minutes and be up and running it. So I'd like to encourage people here who are systems minded to have a look at what we're doing with Ray. It's pretty interesting. So that's all. I could pop up to the top level, but I think I've said everything I want to say.
Naively asking about Ray, is it about smart caching and?
No, that was Spark. No, that was Ray is basically about smart scheduling.
I see.
You got to decide once a little thread, process is kind of really quickly. So you're doing like game search, AlphaGo, and you're going down a game tree, and you realize pretty quickly that was a stupid idea, and so the processor should be liberated to do something else. So you have a dynamic flow graph. There's an actor paradigm, and you decide intelligently which new processor to give which processor to give another job, and then you have a global and local schedulers interacting in a fairly complex way. So there's a big dance of scheduling going on. There's object store and scheduling issues behind the hood.
Okay, now beyond my first question, let's get things moving. Questions?
Yes.
don't know if we need to open this room near Mike, yeah?
I can repeat the question if that helps.
That'd be easier for me. Being active.
So in the Nesterov formulation, I didn't see any structure or geometry about the loss function. So does it apply to all objective functions or some, or does it?
Nothing applies to all objective functions. So yeah, there's some constraints on the objective function there. I mean, that result was just for convex, the Nesterov.
Yeah, so even convex.
But you know, there's mirror descent allows you to get a lot of geometry into there. You know, the mirror descent version, there's the same theory applies to mirror descent. But going beyond that to other kinds of non-convex and other kind of loss functions, you have to do some problem-specific work on that, that's going to be life. That's why we'll always be employed. You have to think about your loss function, and you have to think about the properties of the loss function, and you have to exploit the structure of that, and so on and so forth. Our generic theorems will guide you, but they're not going to just, you know, it's not going to be plug and play for quite some time. I remember Chris Meek back in the back. Yeah.
You just kind of said it's suitably chosen and you get results.
No, this is just it's just a way of formulating what we mean by a rate of convergence.
Well, you know, with the ball coordination, there's a radius for it.
Yeah, epsilon.
Well, you take a perturbation in a ball of size r.
Oh.
Now, what is the relationship between r and what do you need to fire
You want to try to say it more cleanly than I can?
Basically, just pick out to be roughly epsilon, up to some log vector, so that's fine. Epsilon is the final accuracy you want to find. Yeah.
This is more of a meta-level observation in the sense that a bunch of techniques that you mentioned were in the continuous time space, and we have to discretize it because of our computer architectures.
Yeah.
So, do you think there is enough motivation for few of us to start looking at computing in the continuous domain directly? Yeah,
I've been asked that question before, and I actually believe it, yes. I mean, I like this symplectic approach because it's a beautiful way to discretize. But there are some real advantages to working just purely in continuous time. Don't have to worry about some of these issues. There's stability, issues that are handled for you. So, yeah, this is the first time I've worked on something where I feel like, yeah, actually, I would like to have a line-along computer to do this. I think it would be really interesting to explore.
Maybe you'll have an analab next.
Really? Yeah, an analab, yeah. Yeah.
Building on the first part where you spoke about importance of thinking about markets.
Yeah.
I'm curious whether for the optimization landscape, you're also thinking about more generalizations like variational equilibria and...
Yeah, I've thought about that and even tried to work on that kind of thing from time to time. I'm aware, for example, of an interesting literature of not escaping saddle points, but going towards saddle points, right? And there's still actually open problems there of how fast can you approach a saddle point, because the saddle point, game theoretic optimum is what you want to be at, not avoid. And so, yeah, it's just like the next 10 years of my career, I guarantee there'll be a fair amount of more economic stuff, and I already have some ideas. And but that's what I tend to do in life is I say what I'm going to do, and then I just kind of work on it and hope other people will teach me things along the way, because I know very little about serious economics math. I just hope I can learn it quickly. They work with statistics and differential equations, so I should be ready to go. But yeah, I know that MSR has got a lot of people here, and I think that this is kind of I think a lot of people are aware of this, but it's not just about advertised placement. That's not the big application of economics and machine learning together. To me, it is actually the trillion-dollar play of how do you actually really, and this load balancing problem I alluded to is critical, and machine learning people aren't thinking about it at all. They're thinking you're just going to deploy things, and they're not thinking about that. If there's scarcity out there, it's not going to work. In a narrow domain like transportation, yes, they'll do dynamic programming, not send everybody down the same route. But it's a way broader problem, and that's you're not using really any bidding mechanism or economics there.
Even beyond resources, I mean, you deploy a medical system in the world, and it influences the distributions that the probably about the influences of our AI system. The systems actually know that they consider these things.
Yeah.
So, other questions or comments? By the way, whatever if any talk about at all about ClearFlow, which was our predictive modeling traffic around the world now in cities.
Yeah.
I always would just wait patiently. There's always one hand that would go up in the audience. Yep, I'm waiting for your question. And my answer always was, time. Not enough people use Bing Maps to make this a big deal. But at Google, it must be a big problem with Google Maps for the directions and oversubscription of the recommendations.
So I have one funny anecdote too. Since you're telling good funny anecdotes, I want to try to top you. Which is that I was in China now, and I was giving this talk about AI, and everyone's asking me, is all the hype about AI true and all, and I try to tamp it down. But they were pushing on, well, yeah, all your problems, maybe it's going to take decades, but, in pure human imitative AI, we've made such progress. Like, think about natural language translation. It's nearly solved, isn't it? And so, Doug Hofstadter wrote a very nice article, if you haven't seen this, Shallowness of Google Translate, that if you haven't read that, you should read that. Everybody should be aware that just getting to 90 or 95% does not mean we're within 5% of the answer. We're way away from, and he'll give you good examples. Right, but anyway, on the screen behind me, there was supposed to be a panel session, but one of the speakers didn't make it, and was on the screen virtually behind us. I won't name this person. This person was going on about, AI and translation and autonomous this and that, and how translation, we're not quite there yet, but within 10 years, we'll definitely have done it. And there was an automatic translation going on the screen. I think it was Sogo, I think it was the Chinese thing, and it was transcription and translation. So the speaker said at some point, that's a red herring that's a red herring in AI. Okay, does everyone know what a red herring is? Okay, a red herring is a fish. A herring is a kind of fish, and red herring, someone probably knows the etymology better than me, just means something that everyone's paying attention to, you shouldn't pay attention to, it's irrelevant. That's a red herring, don't worry about it. So he says something, I forget the topic, is a red herring in AI. And the translation came up as, that's a red hair in his eye.
Yeah, I mean, again, there's a broader discussion to be had here about the whole the advances in AI. What was it, Minsky? There's a comment that some of these advances are like the excitement that a monkey feels running up into a tree thinking he or she's getting closer to the moon. And it could be just the wrong track or the wrong...
I heard that's not the monkey part. That's a new element. Why is a monkey needed in this particular metaphor?
It implies the type of thinking that's going on.
I see.
Okay, so any other